Right now, at this very moment, somewhere on Earth, ancient ice that fell as snow when your great 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 grandparents were children is beginning its final journey to the sea. A crystal that has waited in frozen silence for over a century is feeling warmth for the first time, releasing a tiny breath of air that last touched the atmosphere when horse drawn carriages filled city streets and gas lamps flickered in windows of homes where families gathered around wood burning stoves, never imagining that their breath, their very exhalations, would someday be preserved in ice and released again in a world transformed. Welcome to Sleep About Science. I'm your sleepy scientist, and tonight, wherever you are in the world, whether you're tucked into bed in Stockholm, watching the northern lights dance across winter skies in sheets of green and purple that seem to whisper secrets from the cosmos, or perhaps lying on a summer evening in Sydney, listening to the gentle rustle of eucalyptus leaves, carrying the scent of distant rain and the promise of cooler air. Or maybe you're somewhere in between, in a bustling city where the sounds of traffic have faded to a distant hum, and the day's worries are beginning to dissolve like sugar in warm tea. We're exploring one of the most profound and quietly dramatic transformations happening on our planet: what happens when glaciers melt. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something beautifully poetic about falling asleep to stories of ice and time, of ancient frozen rivers slowly returning to the sea, of water molecules that have waited centuries for their moment of freedom. Your dreams might carry you to pristine wilderness, where the only sound is the gentle drip of melting ice and the distant call of Arctic birds, or perhaps to vast blue landscapes where ice meets sky in an endless dance of light and shadow. Before we begin our journey into this world of ice and transformation, please make yourself comfortable. Adjust your pillows until they cradle your head just perfectly. Pull your blankets up to whatever feels just right, perhaps up to your chin if the night is cool, or maybe just draped across your body if the air is warm, and let your body settle into that perfect position where you could stay for hours, where every muscle can slowly release its tension from the day. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science, these quiet explorations of the wonders that surround us every moment of every day. Now, imagine for a moment that you could shrink yourself down to the size of a water molecule and travel through time, becoming part of a story that spans not just decades, but centuries and millennia. You begin your journey as part of a snowflake, delicately crystallizing in the frigid air above Greenland sometime in the year 1823. The world below you is vastly different from today. No airplanes cross these skies, no satellites orbit overhead, no research stations dot the ice sheet below. You're not just any snowflake. You're part of a storm system that has traveled thousands of miles, gathering moisture from the North Atlantic, riding air currents that have been shaped by the rotation of the Earth itself, carrying within your crystalline structure the chemical signature of the atmosphere in an age before industrial smokestacks and automobile exhaust changed the very composition of the air we breathe. As you descend through the cold, thin air, you join countless billions of other ice crystals, each one unique, each one a tiny masterpiece of natural geometry. Your six-sided symmetry reflects the hexagonal arrangement of water molecules as they lock into their frozen dance, And though you're impossibly small, you're part of something that will become magnificent and ancient, a glacier. But what exactly is a glacier? At its heart, a glacier is simply a river of ice that moves so slowly you'd need to watch it for years, sometimes decades, to see its motion with the naked eye. Yet this apparent stillness hides incredible power and constant change. Picture the most massive thing you can imagine, perhaps a mountain range stretching to the horizon, or a city skyline with all its towering skyscrapers, or even something as vast as the ocean itself. And then imagine something that can carve through solid granite as if it were soft clay, reshape entire continents over the course of millennia, and hold within itself the climate history of thousands upon thousands of years, preserving in frozen silence the story of volcanic eruptions, meteor impacts, and the gradual dance of atmospheric chemistry across the ages. That's a glacier. Your snowflake settles onto the ice with billions of others, and something remarkable begins to happen. Something so gradual and patient that it defies our usual understanding of cause and effect. Layer by layer, storm by storm, year by year, more snow falls on top of you. The weight begins to accumulate, and you feel yourself being pressed downward, your delicate crystalline structure being compressed and transformed by forces so immense they're almost impossible to comprehend. This process, called fernification, is like nature's very own time machine, a process so slow and methodical that it makes the growth of trees seem hurried by comparison. You're no longer a snowflake with your intricate, lacy structure. You're becoming part of something much larger and more enduring. The air spaces between the ice crystals are being squeezed out. The individual crystals are growing larger and more tightly packed, and you're joining a community of water molecules that will remain together for centuries, traveling as one through the vast, slow rivers of ice that flow across continents. As decades pass in our imagination, you sink deeper and deeper into the ice. The snow above you transforms from fluffy powder that would barely support a bird's footstep to granular snow called fern, dense enough that you might be able to walk on it without snowshoes, and eventually to dense blue tinted glacial ice, so compact that it rings like crystal when struck. The weight above you has become immense. Would imagine having not just an apartment building pressing down, but an entire city neighborhood, thousands upon thousands of tons of ice and snow accumulated over decades of storms, over years when the earth was cooler, when the rhythm of seasons was different, when the very stars above shone down on a world that knew nothing of satellites or radio waves or the industrial hum that now provides the background soundtrack to much of human life. Yet you're held perfectly preserved within this ice, a tiny time capsule carrying with it the atmospheric conditions from that snowy day in 1823, when Andrew Jackson was President of the United States, when Charles Darwin had not yet sailed on the Beagle, when the Industrial Revolution was just beginning to change the chemical composition of the atmosphere. The air bubble trapped near you contains traces of gases from that earlier world, carbon dioxide levels nearly 100 parts per million lower than today, methane concentrations that reflected a world with far fewer domestic animals and rice paddies, and other atmospheric signatures that speak to a planet that was, in many ways, profoundly different from the one we know today. But glaciers aren't static. Despite their appearance of eternal stillness deep within the ice, you're part of a massive slow motion river that flows with a patience that makes human timescales seem like the flutter of a hummingbird's wings. The glacier is flowing, moving toward the sea at a pace so gradual that it would take centuries for you to travel from where you first fell to the glacier's terminus. It's a journey measured not in hours or days, not even in years, but in human lifetimes. Children could be born, grow old, raise families of their own, and pass away peacefully in their sleep while you travel just a few miles within the ice, carried along by forces so vast and slow that they operate on geological time. This movement happens because ice, under enormous pressure, behaves almost like a very thick liquid manage in honey that's been chilled until it barely flows, or thick molasses on a cold winter morning. The bottom of the glacier, warmed by geothermal heat from the Earth's molten interior far below and insulated by thousands of feet of ice above, becomes slightly plastic, slightly yielding. It deforms and flows, carrying everything with it toward lower elevations, following the ancient pathways carved by gravity and topography. Meanwhile, the surface ice remains rigid and brittle, creating the crevasses and seracs that give glaciers their dramatically sculpted appearance, their otherworldly beauty that looks like abstract art carved by forces beyond human imagination. As you flow within the glacier, you're part of an enormous sculptural force, reshaping the landscape with the patience of ages. The glacier beneath and around you is grinding against bedrock, picking up boulders and stones, incorporating them into its icy matrix, and using them as tools to carve valleys wider and deeper. The sound, if you could hear it, would be a constant low grinding, like the world's largest mill, slowly processing stone into flour, creating the fine rock dust that will eventually make soils rich and fertile when the ice finally retreats. U-shaped valleys, those distinctive rounded valleys you might see in places like Yosemite with its towering granite walls, or the Scottish Highlands with their broad sweeping curves, or the fjords of Norway with their dramatic cliffs dropping straight into deep blue water. So are the calling cards of glaciers, where rivers carve sharp V-shaped valleys, cutting down through rock like a knife through soft wood. Glaciers create these broad, rounded corridors that speak of the immense patient power of moving ice, of the ability of frozen water to reshape solid rock, given enough time and pressure. The scale of this carving process is almost beyond comprehension. A single large glacier might move millions of tons of rock over the course of its lifetime, carving valleys thousands of feet deep, creating landscapes that will endure long after the ice has melted and disappeared. The Finger Lakes of New York, the Great Lakes that separate the United States and Canada, countless mountain valleys throughout the world, all were carved or deepened by glaciers during the ice ages, when vast sheets of ice covered much of the northern hemisphere and sea levels were hundreds of feet lower than they are today. But let's fast forward through your icy journey, compressing centuries into moments as we travel through time to reach our present era. It's now the early 21st century, and climate change has begun to accelerate processes that once took geological ages to unfold. The planet's average temperature has risen by just over 1 degree Celsius since the late 19th century, the change that might seem small when you think about the difference between a day that's 70 degrees and one that's 71 degrees. But this seemingly modest change has profound effects on ice, effects that cascade through the Earth's systems in ways that are still being discovered and understood by scientists around the world. You, the water molecule from 1823, are now part of a glacier that's experiencing something unprecedented in its long, slow existence: rapid retreat. The ice that has been your home for nearly 2 centuries is beginning to respond to atmospheric conditions unlike any it has experienced in its millennia long history. The air above is warmer, the ocean below is warmer, and even the bedrock beneath is beginning to change temperature as the insulating effect of thick ice diminishes. What does it mean for a glacier to retreat? It's important to understand that glaciers are always flowing forward, always moving ice from higher elevations toward lower ones, like slow motion rivers that never stop their patient journey toward the sea. Retreat doesn't mean the ice is flowing backward. Instead, it means the front edge of the glacier, called the terminus, is moving backward because ice is melting faster than new ice can flow forward to replace it. It's like a conveyor belt where items are being removed from the front faster than new items are being added at the back, or like trying to fill a bathtub while someone has removed the drain plug. No matter how much water you add, the tub never fills because it's draining faster than you can replace what's lost. The science of glacier melting involves several interconnected processes, each more fascinating than the last, each operating on different timescales and responding to different environmental factors. The most obvious is surface melting, the kind you might observe if you've ever watched an ice cube slowly disappear on a warm summer day, starting at the edges and working inward, leaving behind a small puddle that carries within it all the molecular history of what was once solid ice. When air temperatures rise above the freezing point of water, 32 degrees Fahrenheit or 0 degrees Celsius, that magical temperature where the kinetic energy of water molecules overcomes the hydrogen bonds that hold them in their crystalline lattice, the surface of the glacier begins to melt, creating streams of water that flow across and into the ice. These streams often carry with them fine particles of rock dust, giving them a milky appearance that speaks to the ongoing grinding of rock beneath the ice. But these surface streams don't just flow off the glacier and disappear. Often, they find their way into deep vertical shafts called moulins, a French word meaning mills, because the churning, swirling water resembles the grinding action inside an old flour mill. These moulins can be hundreds of feet deep, vertical tunnels that carry surface meltwater down through the body of the glacier to its very base, like express elevators carrying water from the world of air and sunlight down to the hidden realm where ice meets bedrock. The journey of water through these moulins is both beautiful and violent. The water cascades down through the blue-green ice, wearing the walls smooth, creating cathedral-like chambers within the glacier where the only sounds are the rush of falling water and the occasional crack and groan of the ice adjusting to its changing internal pressures. If you could somehow follow this water on its journey, you descend through layers of ice that represent different periods of the glacier's history, each layer holding within it the atmospheric conditions of the year it was formed, like reading the pages of a book written in frozen water. When this meltwater reaches the base of the glacier, something remarkable happens that fundamentally changes how the glacier behaves. This water acts as a lubricant between the ice and the bedrock below, reducing friction and causing the glacier to slide faster toward the sea. It's as if someone has greased the tracks beneath a massive, slow-moving train, causing it to suddenly accelerate from a walking pace to something much faster, though still slow by human standards. Glaciologists call this process basal sliding, and it can dramatically increase how quickly ice flows toward the ocean. Instead of moving inches per day, parts of the glacier might suddenly start moving feet per day, carrying with them ice that has been accumulating for decades or centuries and delivering it to the terminus where it can calve into the ocean or melt into streams that flow to the sea. But basal sliding isn't just about lubrication. The presence of liquid water at the base of a glacier changes the entire dynamics of how ice moves over bedrock. Water fills cracks and crevices in the rock, and when it refreezes, it expands with tremendous force enough to split solid rock apart. This process, called freeze-thaw weathering, accelerates the erosion of bedrock and creates more sediment that gets incorporated into the ice, turning the glacier into an even more effective carving tool. For glaciers that terminate in the oceanic, called tidewater glaciers, there's another process at work that's both beautiful and dramatic. Submarine melting. Ocean water, even when it's near freezing, is often warmer than the ice at the glacier's terminus. Additionally, the ocean water is salty, which lowers its freezing point and makes it more effective at melting ice even at temperatures below the normal freezing point of fresh water. As relatively warm seawater circulates beneath and around the underwater portion of the glacier, it melts the ice from below and from the sides, undermining the glacier's foundation like waves slowly eroding a sand castle, but on a scale that's almost impossible to imagine. These underwater portions of glaciers can extend hundreds of feet below the surface, creating vast underwater cliffs of ice that are invisible from above, but that play a crucial role in the glacier's behavior. The submarine melting process creates complex underwater topography as different parts of the glacier melt at different rates. Some areas of the glacier's underwater face might be protected from warm currents and melt slowly, while other areas exposed to warmer water or stronger currents might melt much more rapidly, creating overhangs, caves, and unstable structures that can suddenly collapse without warning. This underwater melting sets the stage for one of nature's most spectacular displays, calving. When enough ice has been melted from below, enormous chunks of the glacier, sometimes as large as city blocks, sometimes even larger than entire downtown districts, containing thousands or even millions of tons of ice, suddenly break away from the main glacier and crash into the ocean with thunderous roars that can be heard for miles across the water. These newly formed icebergs carry with them the compressed stories of centuries, ancient air bubbles that once held the breath of pre industrial Earth, particles of dust that fell on the ice during volcanic eruptions decades or centuries ago, and chemical signatures that speak to atmospheric conditions from ages past. Each iceberg is a library of climate history, a frozen archive that will slowly melt as it drifts away from the glacier, releasing its ancient contents into the modern ocean. If you've ever seen footage of glacier calving, you've witnessed one of nature's most dramatically beautiful and terrifying displays of raw power. The event often begins with subtle signs, small chunks of ice falling from the glacier face, perhaps the appearance of cracks or the sound of ice under stress. But these warnings can be deceptive because the main event, when it comes, happens with startling suddenness. The sound begins as a deep groaning, like the earth itself is sighing under some tremendous burden. It's a sound that seems to come from everywhere at once, transmitted through the water, through the ice, through the very bedrock beneath your feet if you're lucky enough to witness such an event in person. Then comes the crackpot, sharp and explosive as a cannon shot, but magnified 1,000-fold, echoing off surrounding cliffs and reverberating across the water like thunder that refuses to fade. Finally comes the roar as millions of tons of ice collapse into the sea, sending waves radiating outward in concentric circles, creating a momentary chaos of white foam and blue-green water shot through, with fragments of ice that catch the sunlight like scattered diamonds. The newly formed iceberg bobs and rolls as it finds its equilibrium, sometimes revealing underwater surfaces that haven't seen daylight for centuries, sometimes rolling over completely to expose ice that was formed when the world was a fundamentally different place. But let's return to you, our water molecule from 1823, because your story is approaching its climax after nearly 2 centuries of patient waiting. You've traveled through the glacier, been compressed and recrystallized, flowed slowly toward the sea, and now you're finally approaching the moment of your release. Perhaps you're part of a surface melt stream, feeling the warmth of the sun for the first time in 200 years. Or maybe you're within a chunk of ice about to calve into the ocean, about to experience the shock of sudden immersion in salt water after your long journey through the frozen landscape. Either way, you're about to rejoin the global water cycle after your extraordinarily long, slow journey through geological time. When you finally melt and become liquid water again, you carry with you more than just H2OK. You hold dissolved minerals scraped from bedrock during your glacial journey, traces of granite and schist, tiny particles of quartz and feldspar that will eventually become part of ocean sediments. You carry with you microscopic particles of ancient dust, perhaps from volcanic eruptions that occurred decades ago, or cosmic dust that settled on the ice from meteor showers that lit up skies when the world was young. Most remarkably, you might still hold within your molecular neighborhood tiny bubbles of prehistoric air, air that contains the exact atmospheric composition from the day you first froze. Scientists prize these ice cores precisely because they're time capsules, holding within their crystalline structure detailed records of past climates, volcanic eruptions, and atmospheric conditions going back not just centuries, but hundreds of thousands of years. By analyzing the ratios of different isotopes in glacial ice, scientists can determine past temperatures with remarkable precision. By measuring the concentration of carbon dioxide and other gases in ancient air bubbles, they can reconstruct the atmospheric chemistry of ages past. By examining microscopic particles trapped in the ice, they can identify major volcanic eruptions, dust storms, and even forest fires that occurred continents away from where the ice was formed. The water you've become, along with millions of other newly melted molecules, each with its own long story of frozen patience, now flows into the ocean, where it begins to have effects that ripple far beyond the immediate area where the glacier terminates. This is where the story of melting glaciers becomes a story about the entire planet's interconnected systems, about how changes in one part of the world inevitably affect every other part, often in ways that are subtle, complex, and sometimes surprising. But first, there's the most immediately understandable effect: sea level rise. When glaciers and ice sheets melt, they add water to the oceans that was previously locked away on land, water that was effectively removed from the ocean system when it first evaporated from the sea surface, fell as snow, and accumulated as ice. It's like adding more water to a bathtub that's already full. The water level has to rise to accommodate the additional volume. The effect might seem small at first. After all, how much difference could one glacier make in an ocean system that covers more than 70% of the planet's surface and contains over 300 million cubic miles of water? But when you consider that there are hundreds of thousands of glaciers worldwide, from small mountain glaciers that might contain only a few million tons of ice to enormous ice sheets like those covering Greenland and Antarctica, that contain enough water to raise global sea levels by tens of feet, the cumulative effect becomes staggering. Currently, melting glaciers and ice sheets contribute about half of the annual sea level rise we observe globally, roughly 1.5 millimeters per year, just from ice melt alone, with the other half coming from the thermal expansion of seawater as it warms. That might not sound like much. 1.5 millimeters is less than the thickness of a penny, but spread across the world's oceans, it represents an enormous volume of water. A millimeter of global sea level rise corresponds to about 360 billion tons of water, roughly equivalent to the volume of Lake Erie, or enough water to supply the entire United States for 3 months. And the rate is accelerating. Satellite measurements and ground based observations show that the rate of ice loss from glaciers and ice sheets has roughly doubled since the 1990s. Some of Greenland's glaciers are retreating at speeds that would have been considered impossible just a few decades ago, losing more ice in single summers than they typically lost in entire decades during the mid 20th century. But sea level rise isn't uniform across the globe, which might seem counterintuitive at first. After all, doesn't water seek its own level? Don't we learn in elementary school that if you pour water into a container, it will settle at the same height everywhere? The reality of global sea level is far more complex and fascinating than this simple model would suggest. The Gelson's surface is actually bumpy, with hills and valleys that can differ in height by over 600 feet from place to place. These variations are created by differences in gravitational pull, ocean currents, wind patterns, variations in water temperature and salinity, and even the ongoing effects of past ice ages. The Earth's rotation creates forces that pile up water in some areas and create depressions in others. Mountain ranges and ocean floor topography influence how water flows and where it accumulates. When a massive ice sheet like Greenland's loses ice, it also loses gravitational pull. The enormous mass of ice that covers Greenland, roughly 680,000 cubic miles of ice, weighing about 2.8 million billion tons, exerts a gravitational attraction that literally pulls ocean water toward it. As this ice melts and flows into the ocean, the gravitational attraction weakens, and the ocean water that was previously drawn toward Greenland begins to flow away from the area. This creates a counterintuitive result. As Greenland loses ice and contributes to global sea level rise, the sea level around Greenland actually drops, while sea levels rise more dramatically in places far from the melting ice. It's as if the ocean is constantly rebalancing itself, with water flowing away from areas of reduced gravitational attraction and toward other regions where gravitational and rotational forces concentrate the additional water. The result is that different parts of the world experience very different rates of sea level rise. Some areas might see sea levels rise twice as fast as the global average, while others might even see sea levels fall slightly, Despite the overall global increase, the Pacific Island nations are experiencing some of the most dramatic effects of this redistribution. Places like Tuvalu, the Marshall Islands, and Kiribati are seeing sea levels rise at rates well above the global average, partly because they're located far from the major ice sheets whose melting creates the gravitational effects that redistribute ocean water. For these low-lying nations, where the highest natural elevations might be only a few feet above current sea level, a rise of just a few feet could make much of their territory uninhabitable. The water molecule that began its journey as a snowflake in Greenland in 1823 might eventually lap at the shores of a coral atoll thousands of miles away, carrying with it the slow motion consequences of a changing climate and becoming part of the rising seas that threaten to submerge entire cultures and ways of life. The effects of glacier melt extend far beyond just adding water to the oceans. Remember that glacial meltwater is fundamentally different from regular seawater. It's fresh, cold, and relatively pure, containing far less salt than the ocean water it's entering. When massive volumes of fresh water enter the ocean, they can disrupt the delicate balance of salt and temperature that drives global ocean circulation patterns, potentially altering weather systems and climate patterns around the world. The ocean's great conveyor belt, the thermohaline circulation system that moves warm water toward the poles and cold water toward the equator, depends on precise differences in water density to maintain its circulation. This system is driven by the fact that warm water is less dense than cold water, and salty water is denser than fresh water. When warm, salty water reaches polar regions, it cools and becomes denser, causing it to sink to the bottom of the ocean and flow back toward the equator along the ocean floor, while warmer water flows in along the surface to replace it. This circulation pattern is crucial for distributing heat around the globe and helping to regulate regional climates. The Gulf Stream, which carries warm water from the Caribbean toward Western Europe, is part of this system and helps keep places like Britain and Norway much warmer than they would otherwise be at their latitude. Without the Gulf Stream, London would have a climate more like that of northern Canada, and much of Scandinavia would be too cold for agriculture. But when large volumes of fresh, cold meltwater enter the system, they can disrupt the circulation. Fresh water is less dense than salt water, so it tends to float on top rather than sink, potentially preventing the formation of the dense salty water that drives the circulation system. This can slow or even shut down parts of the thermohaline circulation, with consequences that could affect weather patterns across entire continents. Some scientists are concerned that continued melting of the Greenland ice sheet could disrupt the Atlantic meridional overturning circulation, which includes the Gulf Stream. Computer models suggest that massive inputs of fresh water from melting ice could weaken or even shut down the circulation system, potentially causing significant cooling in Western Europe even as other parts of the world continue to warm. Imagine the irony: global warming causing so much ice to melt that it actually makes parts of the world colder by disrupting the ocean currents that transport heat around the planet. It's a reminder that Earth's climate system is full of feedback loops and interconnections that can produce counterintuitive results, where the effects of change in one part of the system can manifest in surprising ways in completely different parts of the world. The effects of glacier melt also ripple through marine ecosystems in ways that are still being understood by scientists around the world. When glaciers calve into the ocean, they don't just add water, they add nutrients that have been locked up in ice for decades or centuries. The rock flour, finely ground stone particles created by glacial grinding against bedrock, contains minerals that can fertilize ocean waters, sometimes creating blooms of phytoplankton, the microscopic plants that form the base of the marine food chain. These phytoplankton blooms can be so extensive they're visible from space, creating vast green and blue swirls in the ocean that represent explosions of life, fed by the nutrients released from melting glacial ice. The plankton support small fish and krill, which in turn support larger fish, marine mammals, and seabirds, creating complex food webs that depend on the steady input of glacially derived nutrients. Some Arctic marine animals have evolved to depend specifically on these glacier fed ecosystems. Certain species of seals use glacial ice as platforms for resting and giving birth, requiring the stability of ice that remains in contact with glaciers for extended periods. Walruses depend on sea ice near glacial areas for accessing their primary food sources. Arctic cod, a crucial species in polar food webs, spawn in areas where cold, fresh glacial meltwater meets warmer ocean water, creating the specific temperature and salinity conditions their eggs need to develop properly. Polar bears, of course, represent perhaps the most iconic example of species depending on ice. While they primarily depend on sea ice rather than glacial ice for their hunting platforms, the two types of ice are closely connected. Glacial ice helps maintain the cold conditions that allow sea ice to form and persist, and many polar bear populations depend on areas where glacial fjords create conditions favorable for sea ice formation. As glaciers retreat and sea ice diminishes, these species face increasing challenges that go far beyond simply needing to find new places to rest. The timing of ice formation and melting affects their breeding cycles, their access to food sources, and their ability to travel between feeding and breeding areas. Some populations are already showing signs of stress, with declining body weights, reduced reproductive success, and changes in behavior that suggest they're struggling to adapt to rapidly changing conditions. The retreat of glaciers also reveals landscapes that have been hidden under ice for millennia, creating natural laboratories for scientists studying how ecosystems develop on virgin terrain. As glaciers pull back, they expose bare rock, ancient moraines deposited by earlier advances of the ice, and sometimes even preserved organic material thousands of years old, ancient forests that were overrun by advancing ice during previous climate changes, now revealed as the ice retreats once again. These newly exposed areas become living laboratories for studying ecological successionary, the process by which bare rock gradually becomes colonized by lichens, then mosses, then small plants, and eventually mature ecosystems. Scientists can study plots of land that have been ice free for different lengths of time, creating a timeline of ecological development that shows how life gradually reclaims landscapes freed from ice. The process begins almost immediately after the ice retreats. Wind-blown spores and seeds arrive within weeks or months, carried by birds or by air currents from established ecosystems, sometimes hundreds of miles away. Lichens, those remarkable partnerships between fungi and algae, are often among the first colonizers, able to grow directly on bare rock and slowly breaking it down through chemical weathering, creating the first primitive soils. Pioneer plant species follow, adapted to harsh conditions and poor soils. These plants often have the ability to fix nitrogen from the atmosphere, enriching the soil and creating conditions that allow other species to establish themselves. Over time, shrubs and eventually trees may colonize the area, creating mature forests or grasslands depending on the local climate and conditions. But perhaps most remarkably, retreating glaciers sometimes reveal human artifacts and remains that have been preserved in ice for centuries or even millennia. Alpine glaciers have yielded everything from medieval trade routes, marked by the remains of pack animals and their loads, to 5,000-year-old human remains complete with clothing, tools, and even the contents of their stomachs perfectly preserved by the cold, dry conditions within glacial ice. The most famous of these discoveries is probably Otzi the Iceman, found in the Alps in 1991 when a glacier retreated to reveal his remarkably preserved remains. Dating to over 5,000 years ago, Otzi provided unprecedented insights into Copper Age life, from his clothing and tools to his diet and the circumstances of his death. His discovery was only possible because the glacier that had preserved him for millennia finally retreated enough to expose his resting place. Each of these discoveries provides a window into past climates and human societies, showing us how people lived and traveled in different climatic conditions. But their emergence also marks the loss of the glacial conditions that preserved them in the first place. Many of these artifacts begin to deteriorate rapidly once exposed to air and varying temperatures, making their recovery and preservation a race against time. The melting of glaciers affects freshwater resources in ways that touch the lives of billions of people around the world. Many of the world's great river systems, the Ganges and Indus in Asia, the Colorado in North America, rivers throughout the Andes and the Himalayas, major rivers in Alaska and Western Canada, depend partially or significantly on glacial meltwater for their flow, especially during the driest times of the year when other water sources are at their lowest levels. These glaciers act like massive, slow release water storage systems, accumulating snow and ice during cold periods and releasing water gradually during warmer times. This natural regulation helps maintain river flows during dry seasons, provides irrigation water for agriculture, and supplies drinking water for urban areas that might otherwise face severe shortages during drought periods. The timing of glacial melt is crucial for these systems. In many mountain regions, glaciers melt most rapidly during the warmest months, which often coincide with the growing season when farmers need water for their crops. This natural timing has allowed agricultural systems to develop that depend on the predictable seasonal release of glacial meltwater, supporting food production for hundreds of millions of people. As glaciers shrink and eventually disappear, they initially provide more water than usual to these river systems, a temporary boost that might seem beneficial, but that actually represents the glacier consuming itself, spending down its accumulated capital of ice. It's like withdrawing money from a savings account faster than you're making deposits. You might have more cash available in the short term, but eventually the account will be empty. Once the glacier is gone, the rivers lose this crucial source of steady water supply, potentially leaving billions of people with reduced access to fresh water during the driest times of year. The seasonal timing of water availability changes as well, with more water available during wet seasons when it's least needed, and less water available during dry seasons when it's most crucial. In Peru, entire communities that have depended on glacial streams for generations are already experiencing water shortages as local glaciers disappear. Villages that have existed in the same locations for centuries are being forced to relocate or drastically change their way of life as the water sources that made their locations viable simply disappear. In the Himalayas, changes in glacial melt patterns are affecting the timing and volume of water available to some of the world's most densely populated river valleys. The Ganges and Indus river systems, which support over 1 billion people between them, could face significant water supply challenges as Himalayan glaciers continue to retreat. The implications extend far beyond just water supply buyers. These river systems support agriculture that feeds much of South Asia, and changes in water availability could affect food security for enormous populations. The pace of glacial retreat varies dramatically around the world, influenced by local climate conditions, ocean temperatures, glacier size and shape, and many other factors. But almost everywhere scientists look, the trend is toward faster melting and retreat. Some smaller glaciers have disappeared entirely within human lifetimes, leaving behind only bare rock and small lakes where there were once rivers of ice. Glacier National Park in Montana, which once contained over 150 glaciers when it was established in 1910, now has fewer than 30, and many of those are projected to disappear within the next few decades if current trends continue. The park's glaciers are not only shrinking in area, but also thinning dramatically, losing thickness as well as extent as warmer temperatures affect the entire depth of the ice. The speed of change is perhaps most dramatic in the Arctic, where temperatures are rising faster than anywhere else on Earth. This phenomenon, called Arctic amplification, occurs because of feedback loops involving ice and reflection. Ice and snow reflect sunlight back to space, helping keep polar regions cool. This reflection, called albedo, is one of the most important factors regulating Earth's temperature. But as ice melts and darker rock or water is exposed, more sunlight is absorbed rather than reflected, leading to more warming, which leads to more melting, which leads to more dark surface exposure, and so on. It's a positive feedback loop that can accelerate change once it gets started, like a ball rolling down a hill that picks up speed as it goes. Some Arctic glaciers are retreating so rapidly that they're breaking records year after year, with retreat rates that were considered impossible just a few decades ago. Jakobshavn Glacier in Greenland, one of the fastest moving glaciers in the world, has been retreating at unprecedented rates, contributing more to global sea level rise than any other single glacier on Earth. The sound of this glacier calving can be heard from over 100 kilometers away, a deep, rumbling thunder that speaks to the enormous scales of energy and mass involved in glacial retreat. Local populations describe the sound as unlike anything else, not quite like thunder, not quite like an earthquake, but something that seems to come from the very foundations of the earth itself. The retreat of Jakobshavn and other major Greenland glaciers has been so rapid that it's clearly visible in satellite imagery, with the glacier front retreating several kilometers in just a few years. Time-lapse videos created from satellite images show decades of retreat compressed into seconds, making visible the kinds of changes that would normally take place over timescales too long for human observation. But even as we discuss the dramatic changes happening to glaciers worldwide, it's important to remember the vast of timescales involved in their formation and the profound patience required to understand their full significance. The ice that's melting today began accumulating centuries or millennia ago during climate conditions very different from our current situation. In some sense, we're witnessing the end of the last ice age, accelerated and complicated by human influence on the climate system. The last major ice age reached its peak about 20,000 years ago, when ice sheets covered much of northern North America and northern Europe, and glaciers were much more extensive in mountain ranges around the world. Sea levels were about 400 feet lower than today because so much water was locked up in ice on land. The Great Lakes region was buried under ice sheets over a mile thick. Much of what is now the northern United States was a landscape of ice rock and tundra. As the climate warmed at the end of the Ice Age, these enormous ice sheets gradually retreated, leaving behind the landscapes we know today. The process took thousands of years, with the ice retreating in fits and starts, sometimes advancing again during brief cold periods, but overall following a pattern of gradual warming and ice loss that continued until a few thousand years ago, when the climate stabilized into the relatively stable conditions of the Holocene epoch. The glaciers that exist today are the remnants of that much more extensive Ice Age glaciation, survivors that have persisted through thousands of years of gradual climate change. But now they're facing rates of temperature change that are much faster than anything they've experienced in their long history, changes that are happening over decades rather than millennia. The loss of glaciers represents more than just environmental change. It's the loss of archives, libraries written in ice that contain detailed records of Earth's climatic history. When a glacier melts completely, all the information stored in its layers, records of ancient volcanic eruptions that can be identified by ash layers in the ice, changes in atmospheric composition recorded in ancient air bubbles, evidence of past droughts, and abundant periods preserved in the annual layers of ice accumulation is lost forever. It's as if someone were burning books faster than we could read them, each volume containing unique and irreplaceable information about our planet's past. Scientists are racing to extract ice cores from endangered glaciers before they disappear completely, creating frozen libraries in research facilities around the world where future generations of scientists might be able to read the climate stories preserved in ancient ice. Yet there's also something profoundly moving about understanding that the water we drink, the rain that falls on our gardens, the streams that flow through our cities, might once have been part of a magnificent glacier that carved valleys and shaped landscapes over thousands of years. The water cycle connects us all to these ancient rivers of ice and to the geological processes that have shaped our planet over deep time. Water is constantly cycling through different states and locations, spending time as vapor in the atmosphere, as liquid in rivers and oceans, as ice in glaciers and snowpacks, and even as groundwater deep beneath our feet. The average water molecule spends about 9 days in the atmosphere, several years in rivers and lakes, thousands of years in glaciers, and potentially millions of years in deep groundwater. But individual molecules can have journeys that are much shorter or much longer than these averages. The water molecule we've been following through its glacial journey might now begin a new adventure, perhaps evaporating from the ocean's surface and becoming part of a cloud system, traveling over land, falling as rain in a tropical forest, where it becomes part of a river system that eventually carries it back to the sea. Or it might become part of groundwater, slowly filtering through rock and soil over decades or centuries before emerging in a spring that supplies drinking water to a city thousands of miles from where it first entered the ground. This endless cycling of water through different states and locations is one of the most beautiful and essential processes on our planet. Water connects all life, all landscapes, all climates. It flows from the highest peaks to the deepest ocean trenches, from the smallest droplets in morning dew to the vast ice sheets that cover entire continents. Understanding the melting of glaciers helps us appreciate our place in this grand circulation, our role as temporary participants in cycles that have been operating for billions of years. As you lie there listening, perhaps you're beginning to feel the weight of sleep settling over you like a gentle blanket, soft and comfortable, and perfectly suited to your body's needs. That's perfectly wonderful. Let your mind wander through landscapes of ice and stone, through the patient geography of glacial valleys carved by centuries of slow moving ice, through the quiet transformation of snow to fern to ice, to melt water to sea. There's something deeply calming about these vast, slow processes, these changes that happen on timescales so much larger than our daily worries and concerns, so much more patient than our human rush through life. The story of glacial melt is ultimately a story about connection, how the snowfall in one place and time becomes the sea level rise in another place and time, separated by decades or centuries. How the climate conditions of centuries past influence the water resources of today, how the actions of one generation shape the world inherited by future generations. It's a reminder that our planet is a single interconnected system where changes in one part inevitably affect all the others, often in ways that take time to become apparent. Modern technology allows us to monitor glacial change with unprecedented precision, giving us insights into processes that would have remained invisible to previous generations. Satellites equipped with laser altimeters can measure changes in ice thickness across entire ice sheets with accuracy measured in centimeters. Radar systems can peer through ice to map the bedrock beneath glaciers, revealing the hidden topography that influences how ice flows and where it's most vulnerable to melting. GPS stations placed directly on glaciers record their motion with centimeter level accuracy, showing not just how fast glaciers are moving, but also how their speed changes seasonally and in response to factors like temperature and rainfall. Time lapse cameras positioned to view glacier termini capture years of change in seconds, compressing decades of glacial retreat into brief, startling videos that make visible what would otherwise happen too slowly for human perception. This technological monitoring has revealed that glacial retreat is not a steady linear process like water draining from a bathtub at a constant rate. Instead, it's full of accelerations, pauses, and sometimes even temporary advances. Some glaciers retreat steadily for years and then suddenly accelerate as they encounter changes in their underlying bedrock, or as warming ocean water reaches new parts of their terminus, or as surface melting increases the amount of lubricating water reaching the glacier's base. Others might pause their retreat for years, as cooler conditions temporarily prevail, or as changes in snowfall patterns provide more ice accumulation in their upper reaches, only to resume rapid melting when conditions change again. These variations remind us that glaciers are complex systems responding to multiple environmental factors, not simple ice cubes melting uniformly in response to temperature alone. The complexity of glacial behavior means that predicting exactly how fast ice will melt and sea levels will rise remains one of the great challenges in climate science. Computer models must account for countless variables: air temperature and how it varies with altitude and season, ocean temperature and how it changes with depth and location, precipitation patterns, and whether snow falls as rain or snow, wind patterns that affect both temperature and snow distribution, the shape of the bedrock beneath the ice, the presence or absence of liquid water at the glacier's base, the rate at which ice flows from accumulation areas to melting areas, and many others. Each glacier responds differently to changing conditions based on its unique combination of these factors. A glacier that terminates on land will behave very differently from one that terminates in the ocean. A glacier flowing over rough, irregular bedrock will behave differently from one flowing over smooth bedrock. A glacier in a maritime climate with lots of winter snow and mild summers will respond differently to warming than one in a continental climate with little precipitation and extreme seasonal temperature variations. What scientists can say with confidence is that the overall trend is clear. Glaciers worldwide are losing mass faster than they're gaining it, and this imbalance is accelerating. The question isn't whether glaciers will continue to retreat and contribute to sea level rise, but rather how fast this will happen and what the regional and local effects will be. Even the most conservative estimates suggest continued significant ice loss and sea level rise, while more aggressive scenarios suggest changes that could dramatically reshape coastlines around the world. Some regions are experiencing more dramatic changes than others, creating a complex global pattern of glacial retreat. The Antarctic Peninsula, the northernmost part of Antarctica, has seen some of the most rapid glacial retreat on Earth, with enormous ice shelves collapsing in spectacular fashion. The Larsen B ice shelf, which had been stable for over 10,000 years, disintegrated in just a few weeks in 2002, creating thousands of icebergs and opening up new areas of ocean that had been covered by ice since the end of the last ice age. The collapse of ice shelves like Larsen B doesn't directly contribute to sea level rise because the ice was already floating on the ocean like ice cubes in a glass of water. But these ice shelves act as buttresses, holding back the flow of glacial ice from the land behind them. When they collapse, the glaciers they were restraining can accelerate their flow toward the ocean, contributing to sea level rise as they deliver more land based ice to the sea. But Antarctica as a whole presents a more complex picture than simple ice loss. While the peninsula and West Antarctic ice sheet are losing mass rapidly, parts of East Antarctica are actually gaining ice as warmer air carries more moisture inland, leading to increased snowfall in the interior of the continent. The net effect is still ice loss, but it's a reminder that our planet's response to climate change involves complex regional patterns that don't always match simple expectations. The situation is further complicated by the fact that parts of the West Antarctic ice sheet rest on bedrock that lies below sea level, making them potentially unstable as warming ocean water can reach the base of the ice sheet and melt it from below. Some scientists are concerned about the possibility of rapid, irreversible collapse of parts of the West Antarctic ice sheet, which could contribute several feet to global sea level rise over the course of decades rather than centuries. Greenland tells a clearer story of accelerating ice loss. This enormous island, mostly covered by ice up to 2 miles thick, is losing ice mass at an accelerating rate that's clearly visible in satellite measurements. In recent years, Greenland has lost more ice in single summers than it typically lost in entire years during the 1990s. The ice sheet is experiencing both increased melting at the surface and accelerated flow of ice toward the sea, a double effect that's causing rapid changes to an ice sheet that had been relatively stable for thousands of years. The surface of the Greenland ice sheet is experiencing melting at elevations that previously stayed frozen year round. Melt ponds, lakes of liquid water, that form on the surface of the ice sheet during summer are appearing at higher elevations and persisting for longer periods each year. These melt ponds are darker than the surrounding ice, so they absorb more sunlight and accelerate the melting process, creating another positive feedback loop that can amplify the effects of warming. Some of these melt ponds drain suddenly when the meltwater finds or creates channels through the ice to the base of the ice sheet, a process that can happen in just a few hours and can drain lakes containing millions of gallons of water. When this water reaches the base of the ice sheet, it acts as a lubricant that increases the speed at which ice flows toward the edges of Greenland, accelerating the delivery of ice to the ocean where it can melt or calve as icebergs. The visual evidence of these changes can be stunning and sobering. Comparing photographs of the same glaciers taken decades apart reveals transformations so dramatic they're almost hard to believe. Glaciers that once filled entire valleys now exist only as small remnants clinging to the highest peaks. Coastlines that were once fronted by walls of ice now show bare rock and open water. Valley floors that were once covered by hundreds of feet of ice now host rivers and lakes where there was once only frozen landscape. These changes are happening within human lifetimes, allowing individuals to witness transformations that would normally take place over geological time periods. Inuit elders in Greenland speak of hunting and fishing areas that have completely changed within their memory, of sea ice conditions that their fathers and grandfathers described, but that no longer exist, of coastal erosion in places where protective ice barriers have disappeared, allowing ocean waves to attack previously protected shorelines. For indigenous communities in polar regions, glacial retreat and sea ice loss represent not just environmental change, but the transformation of cultural landscapes that have remained relatively stable for generations. Traditional knowledge about ice conditions, wildlife behavior, and seasonal patterns, knowledge passed down through oral tradition over centuries, must now be constantly updated as environmental conditions change faster than ever before in living memory. Traditional hunting and travel routes that depended on predictable ice conditions are becoming unreliable or dangerous. Species that were once common in certain areas are moving to new locations or changing their behavior in response to changing ice conditions. The very vocabulary that describes different types of ice and ice conditions is becoming obsolete as traditional ice types disappear or occur at different times and places than they did in the past. The retreat of glaciers also affects global weather patterns in subtle but significant ways that scientists are still working to understand. Ice sheets and glaciers influence atmospheric circulation by creating persistent high pressure systems over their surfaces, areas where cold, dense air descends and creates stable weather patterns. As these ice masses shrink, they alter wind patterns and storm tracks in ways that can affect weather thousands of miles away. The loss of Arctic sea ice, which is closely related to glacial retreat, because both are responses to warming polar temperatures, appears to be influencing the behavior of the jet stream, the high altitude river of air that guides weather systems across the northern hemisphere. Some research suggests that as Arctic ice diminishes, the jet stream becomes more wavy and unstable, potentially leading to more frequent extreme weather events, heat waves, droughts, floods, and severe storms at mid latitudes. These connections between ice loss and weather patterns are complex and still being studied, but they illustrate how changes in polar ice can have far reaching effects on human societies far from polar regions. A glacier retreating in Greenland might contribute to changes in atmospheric circulation that affect rainfall patterns in Africa or storm tracks that influence hurricane development in the Atlantic or heat waves that affect agriculture in Europe. As we contemplate these vast changes happening to our planet's ice, it's natural to feel both amazement at the scale of natural processes and concern about the rate of change we're witnessing. But there's also something deeply moving about understanding our connection to these ancient rivers of ice, to the patient accumulation of snow over centuries, to the slow transformation of precipitation into ice and eventually back to liquid water. The story of glacial melt reminds us that we live on a dynamic planet where everything is connected across space and time. The breath you exhale might someday become part of a cloud that drops snow on a distant glacier, if any glaciers remain to receive it. The water you drink might have flowed through glacial streams decades ago, carrying with it minerals and nutrients that originated in rock ground down by the patient movement of ice over stone. The landscapes we find most beautiful, the valleys, lakes, and mountains that inspire us and provide us with a sense of peace and wonder, were often carved by glaciers during past ice ages, sculpted by the slow but irresistible force of moving ice. Even as current glaciers retreat, they leave behind landscapes of stunning beauty, evidence of the power of ice to shape the Earth's surface over long periods of time. If you're still awake and listening, feeling perhaps the gentle tug of sleep beginning to pull at your consciousness, you might imagine yourself once again as that water molecule we followed earlier, finally free from your centuries long journey through glacial ice, now part of the ocean's vast circulation, carrying with you the history of your time in the ice and ready to begin new adventures in the endless cycling of water around our planet. You might evaporate from the ocean's surface on a warm, sunny day, rising through the atmosphere as invisible water vapor, joining billions of other water molecules in the constant upward movement of moisture from sea to sky. You might become part of a cloud, condensing around microscopic particles of dust or salt, growing from a tiny droplet into part of a larger water drop that eventually becomes heavy enough to fall as rain. Perhaps you fall on a forest, becoming part of a stream that flows through valleys carved long ago by glacial ice, carrying nutrients to plants and animals, supporting ecosystems that depend on the steady flow of fresh water. Perhaps you soak into soil and become part of groundwater, slowly filtering through rock and earth over years or decades before emerging in a spring that supplies drinking water to a city, becoming part of the bodies and lives of countless organisms before eventually finding your way back to a river and then to the sea. Or perhaps, if the climate cools again in the distant future, you might once again fall as snow on a high mountain peak, beginning another long journey through the formation of glacial ice, becoming part of a new glacier that will slowly carve new valleys and create new landscapes over thousands of years. The water cycle is truly endless, with no beginning and no end, connecting all times and places through the constant movement of H2O through its different phases and locations. This endless cycling of water through different states and locations is one of the most beautiful and essential processes on our planet. Water connects all life, all landscapes, all climates. It flows from the highest peaks to the deepest ocean trenches, from the smallest droplets in morning dew to the vast ice sheets that cover entire continents. Understanding the melting of glaciers helps us appreciate our place in this grand circulation, our role as temporary participants in cycles that have been operating for billions of years and that will continue long after our brief human moment has passed. As you settle deeper into comfort, perhaps drawing your blankets up a little higher, adjusting your pillow to that perfect position that cradles your head just right, you might think about the incredible privilege of living on a planet with such dynamic, beautiful, and complex systems. Despite all the changes and challenges our planet faces, despite the rapid retreat of glaciers and the rising of seas, Earth remains an extraordinarily rare and precious place, a world with liquid water, with ice, with life, with the delicate dance of climate systems that make our existence possible. The glaciers may be retreating, but they leave behind landscapes of stunning beauty, valleys carved with the patience of millennia, lakes formed by their ancient movements, and stories written in stone about the planet's long history of climate change and geological transformation. Even as we witness rapid change that's unprecedented in human experience, we can find comfort in understanding our connection to these deep, slow processes that operate on timescales much larger than human concerns. Our participation in cycles that connect us to all life and to the very geology of our planet. The retreat of glaciers is part of a larger story about Earth's climate system, about how our planet responds to changes in atmospheric composition, about the complex feedbacks between ice, ocean, atmosphere, and life itself. It's a story that's still being written, with each day bringing new measurements, new observations, new understanding of how our planet's systems respond to change. Scientists around the world continue to monitor glaciers with increasingly sophisticated instruments, tracking not just their retreat, but also changes in their internal structure, their flow patterns, their response to seasonal variations in temperature and precipitation. Research stations on the ice provide detailed measurements of conditions that affect glacial behavior, while satellites provide a global perspective on changes happening across entire ice sheets and glacier systems. This research is crucial for understanding not just what's happening now, but what might happen in the future under different scenarios of climate change. The information stored in glacial ice provides essential context for current changes, showing how glaciers have responded to past climate variations and helping scientists understand the full range of glacial behavior under different conditions. But perhaps most importantly, the study of glaciers reminds us of the deep connections that link all parts of the Earth system. The snow that falls on a remote glacier becomes the meltwater that affects sea levels around the world. The ice that forms over centuries becomes the fresh water that can alter ocean circulation patterns. The glaciers that carve valleys become the landscapes that shape weather patterns and provide habitat for countless species. Understanding these connections helps us appreciate both the stability and the fragility of the systems that support life on Earth. For thousands of years during the Holocene, Earth's climate was remarkably stable, allowing human civilization to develop agriculture, build cities, and create the complex societies we know today. But that stability depended on a delicate balance of factors, including the presence of large ice sheets and glacier systems that helped regulate global temperature and sea level. As that balance shifts, as glaciers retreat and ice sheets lose mass, we're entering a period of change that will likely continue for many decades or centuries, regardless of what actions we take now. The ice that's melting today represents centuries of snow accumulation, and even if we could instantly stop all warming, the ice sheets and glaciers would continue to adjust to current conditions for many years to come. This long term commitment to change makes adaptation as important as mitigation in dealing with the consequences of glacial retreat. Coastal communities around the world are already beginning to plan for higher sea levels, developing strategies for protecting infrastructure, modifying building codes, and in some cases planning for managed retreat from the most vulnerable areas. Water resource managers in regions that depend on glacial meltwater are developing strategies for storing water during abundant periods and managing demand during times of scarcity. Agricultural systems are adapting to changing patterns of water availability, developing more efficient irrigation methods, and shifting to crops that are better adapted to new conditions. But adaptation strategies must be developed with an understanding of the long timescales involved in glacial processes. Changes that are set in motion today by glacial retreat might continue to unfold over many decades or centuries. Planning for these changes requires thinking on timescales that extend far beyond typical political and economic planning horizons. The story of glacial retreat is ultimately a story about times and about how the actions and conditions of the past shape the present, and how our current actions will influence the future in ways that extend far beyond our own lifetimes. It's about the patience of geological processes and the speed of human induced change. It's about the weight of centuries of accumulated snow and the lightness of water vapor rising into the atmosphere. It's also a story about about how local changes in temperature and precipitation can have global consequences, about how processes that seem slow by human standards can reshape entire landscapes, about how individual water molecules can be part of systems that operate on planetary scales. As you lie there in the comfort of your bed, feeling the gentle pull of sleep beginning to take hold, let your mind rest in the vastness of these processes, in the patient transformation of ice to water, in the endless cycling of H2O through the Earth system. There's something deeply peaceful about understanding our place in these ancient cycles, about knowing that we're part of something much larger and older than our individual lives. The water in your body has been part of clouds and rain, rivers and oceans, ice and snow, countless times throughout Earth's history. The oxygen you breathe has been part of the atmosphere for billions of years, cycling through the bodies of countless organisms, sometimes locked in rock or ice, sometimes free in the air, always moving through the great cycles that sustain life on our planet. Sleep well tonight, wherever you are in the world, whether you're listening to the gentle patter of rain that might once have been glacial ice, feeling the humid air of a summer evening that carries moisture evaporated from distant oceans, or looking out at city lights reflected in water that has traveled unimaginable distances to reach you. Remember that you are part of something magnificent and ancient, the circulation of water around our beautiful planet, the slow dance of ice and sea and atmosphere that makes life possible. As you drift off to sleep, you might dream of vast landscapes of ice and stone, of the patient carving of valleys by glaciers that moved with the slowness of geological time, of meltwater finding its way through ancient channels to the sea, of the endless cycling of water through all the places it can exist on our dynamic, ever changing, beautiful Earth. Thank you for joining me on this journey through ice and time, through the patient processes of glacial formation and the accelerating processes of glacial retreat. Your curiosity and attention honor both the science we've explored and the magnificent planet we call home. Your willingness to learn about these complex systems, to understand the connections between seemingly distant processes, makes you part of the solution to the challenges our changing planet faces. Sweet dreams, and may your rest be as peaceful as snowfall accumulating on distant peaks, as gentle as meltwater flowing through mountain meadows, carrying the minerals and stories of ancient rock, as deep and restorative as the ancient ice that holds within itself the memory of countless seasons, countless storms, countless quiet moments when snow fell on ice in places far from human eyes, building the glaciers that have shaped our world and that continue, even as they retreat, to teach us about the deep connections that link all parts of our remarkable planet. I'm your sleepy scientist, and this has been Sleep About Science. Until next time, wherever you are in the world, in whatever time zone you call home, surrounded by whatever weather patterns are blessing or challenging your part of our shared planet tonight. Sleep well, rest deeply, and dream peacefully of the magnificent, ancient, ever changing world of which we are all part.